You know, my grandfather used to say, do not render stuff which the viewer cannot see. True story. What is up, everybody? Today we're going to implement a performance optimization using a pretty well-known algorithm called frustum culling. The idea is very simple. We don't want to send stuff to the GPU, which will eventually get clipped away. It's just a waste of cycles. Better take care of that on the CPU before you do the render. We will have two methods to do frustum culling. The first one is very simple. The second builds on top of the first, so it's a bit more complex, but may also perform better. Okay, so let's see an example using Blender. What we have here is a small scene. This monkey right here represents the viewer, and we have several objects here, right? We have this helicopter, a couple of dragons, a jeep, and a bunny. And we can also see the view frustum here, and as you already know, what goes into the current frame is only the stuff which is inside, or at least partially inside the view frustum, and everything else gets clipped away. Okay, so out of all of these objects, we can only see this dragon right here, which is inside, and everything else is outside, right? The dragon is beyond the far Z of the view frustum. The helicopter and the jeep are too much to the left and right, and the bunny is behind the viewer, so obviously we cannot see that. And the view frustum itself, in terms of the shape, is defined by several parameters. First of all, we have the field of view angle, okay, which determines how wide or narrow the frustum is. So it can bring in more objects if we make it wider, or less if we make it narrower. And we also have the aspect ratio, which is basically the ratio between the width and height of this rectangle, which must match the dimensions of the window, otherwise the image will be distorted. And we have the near Z and the far Z, which tells us the range inside the 3D world that is visible to the viewer. Now, usually the near Z is a very small number, but the far Z, you can play with it. I mean, it can be like 100 or 1000. So there's a big flexibility there to determine how far you can see. And the perspective projection matrix is created by combining all of these parameters together. Okay, so the field of view angle, the aspect ratio, and the near and far Z. Now we're going to study frustum culling in the context of terrain rendering, but obviously you can take the same technique and apply it to regular objects as well. Now for the terrain, we have a grid of patches, and I'm using the GeoMip mapping algorithm, which I covered in the last 3 videos, but basically any algorithm that divides the terrain into multiple patches should work the same. And what we have here is the camera and the target vector. So we have a view frustum as well. Okay, so right now we're in a top-down view, so we can only see 2 dimensions, the X and the Z, but obviously the frustum also has a Y component. What we expect in this case is to render only the patches that at least partially intersect with the frustum. Okay, so all of these guys right here. Okay, so the question that we need to ask ourselves at this point is, how come things are clipped away in the first place? And for that, I'd like to do a really quick recap of the 3D pipeline. We went over this with great detail in previous videos, so you should definitely check that out. And you know that we start in the local space of the object, and we do a couple of transformations to move the object to the world and then to the view. Now, these transformations may include scaling, rotation, and translation. The next step is to apply the perspective projection transformation. Now, as you already know, in order to get the perspective 3D effect, we need to divide by the Z, which we cannot do inside matrix multiplication. So what we do is to separate perspective projection into 2 steps. First of all, we have the perspective projection matrix at this stage, and later on in the pipeline, we divide by the W in a stage which is called perspective division, which is done automatically by the GPU. Now, multiplying by the perspective projection matrix takes us from view space into clip space. And the reason that this is called clip space is because this is where the clipper works. The clipper is a fixed function unit in the GPU, which clips the X, Y, and Z components of the clip space coordinate between the minus w to plus w component of the same coordinate. And the result is that following perspective division, where we divide the output from the clipper by the w component, the x, y, and z are now between -1 and 1. And at this stage, it is very easy to transform the x and y to screen space, basically coordinates of pixels on the screen, and the z itself is usually transformed to 0 to 1 and goes into the depth buffer. Just to give you a general idea of what the clipper can do, as we can see here, we can see the range between -w and w plus w. The clipper needs to work on all the vertices of a single primitive or triangle together. So if all the vertices are outside of the valid range, the triangle is clipped away. Okay, so in this case, we have one triangle which is too far to the left, or what we call the left clipping plane, so it is dropped. And we have another which is below the bottom clipping plane. One is to the right of the right clipping plane, and another triangle is clipped because it is above the top clipping plane. Now this triangle is okay, so it is sent to do the usual processing. And here we have two interesting cases where the clipper needs to actually generate new vertices. As you can see right here, this triangle is partially inside the frustum, so the clipper needs to generate two vertices here instead of those two. And in some cases, the clipper needs to generate another triangle. For example, in this case, we started with one triangle and we ended up with two. Okay, so this brings us to the first method called view space culling, or culling inside view space. The idea is that we take a point in view space, and it's not just any point, it's part of a bounding box of the object, or in our case, a patch, and we'll see that in a second. We apply the perspective projection transformation on this point, and we say that the point is inside the view frustum only if all the following conditions are true. Okay, so the x, y, and z components must be within the range of -w to +w. If one of these conditions fail, we know that the point is outside the view frustum. Okay, so if the first two conditions are true, but let's say that z is greater than w, then we know that the point is kind of in front of the camera, but it is beyond the far z, which means that it is clipped away. In the general case, we need to create a bounding box around the object, and excuse me for the poor diagram, but imagine that this object also has a depth. So the bounding box has 8 vertices. So we need to call the object if all the corners of the bounding box fail the above conditions. But if at least one of them passes, then we say that the object is inside the view frustum, so we will render it as usual. Okay, so let's see some code. This is the render function of the Geomip grid class. And previously it only needed the camera position, which we used to update the LOD manager from the previous video. We now take an additional parameter, the view projection matrix, okay, the combined view and projection matrices. So we can multiply the vertices of the patch by the view projection matrix and take them directly from world space into clip space. And we have another function called here, is patch inside view frustum view space, okay, because this is the view space method, and this function takes the bottom left corner of the patch along with the view projection matrix. And if this function returns false, we basically skip the draw call, so the patch is not rendered. And we also print 0 here, and this is just for debugging. I will show you that in a second. If the function returns true, we print 1 and we continue as usual. So let's see what the function does. It defines the 4 corners of the patch. We use the patch size and the world scale to set the x and z coordinates, and we take the height from the terrain. Okay, so we are not using a bounding box here. So what we do is to extract the height from the height map at the 4 corners of the patch, and this is what we use for frustum culling. We can also use a bounding box, and actually we will use a bounding box in the next method. Here I'm showing you something different, and you can play with it and decide what works best for you. So now that the 4 corners are defined, we call isPointInsideViewFrustum on each point, passing in the view projection matrix. And if at least one of these function returns true, then we say that the patch is inside the viewFrustum. So let's see what this function does. And as expected, this is exactly as we saw in the background section. We need to extend the point to homogeneous coordinates, okay, by adding 1 for the W. Okay, so we have a 4D vector for the position, and we calculate the clip space position by multiplying the view projection matrix by this point. And now we say that the point is inside the viewFrustum if all of these conditions are true. And you can also reverse this check, so you will exit from this function earlier. Basically, this will be is point outside of the viewFrustum if one of them fails, and then you can exit. But then it means that you will need to change these conditions to an end. You will need to check or to verify whether all the points are outside of the viewFrustum in order to say that the patch is inside or outside. So now let's run this, and as you can see, it works very nicely. We can see the printing on the left-hand side. As I move the camera to the left, we are seeing less and less patches, and it is also reflected in this printing right here. Right now, we can only see one column on the left-hand side of the terrain. Okay, if we move the camera to the right, we can see the shape of the frustum. Okay, moving on to the second method, which is called world space culling. Okay, so we had view space culling in the first method, and this is world space culling. And the reason that this should be more optimized is that the vertices are already defined in world space. So if we can do the culling here, rather than transform them to clip space, so actually the first method should have been called clip space culling, but I've just thought about it. Okay, so we can actually save us the transformation from world to clip space and do the dead or alive checks of the clipper directly in world space. We just need to do some preparations before we do the test rather than go to it directly as in the first method. But when you have a lot of objects or a lot of patches, this is probably worth it. Okay, so these are the same conditions from the first method. And as you can see, I've added C in subscript just to underline the fact that this is a clip space test. And let's take, for example, X is less than or equal to W. Okay, this one right here. We can move the W to the other side of the inequality. And so we get X minus W is less than or equal to 0. Now, what exactly are X and W in clip space? Okay, if we have the perspective projection matrix like that, and we have the view space vector, the X, Y, Z, and W components of the clip space coordinate are calculated by doing a dot product between the corresponding row of the perspective projection matrix by the view space vector. Okay, so as we can see here, we need to multiply M11 by X plus M12 by Y plus M13 by Z. And finally, we can add M14 because this is 1. And then we do the same for all of these guys. Okay, so if we go to the condition from the previous slide, we are right now here. We can extract or replace, let's say replace X and W by their corresponding calculations from here. And then with a few shuffling around of the terms of the expression, and be careful here because we have minus here, so we need to put this group of elements or terms in parentheses, we can get to this expression right here. Okay, so for example, xv multiplied by m11 from here minus, because we have the minus here, m41. And we do the same for y, z, and w. So what is this expression? This is actually a dot product between the view space vector, right, x, y, z, w in view space, by another vector, which is calculated by subtracting the fourth row of the matrix from the first row, right? You can see M11, M12, M14, M13, M14. This is the first row of the matrix minus the elements from the fourth row. So the bottom line is that if this dot product turns out to be less than or equal to 0, we say that P is on the left-hand side of the right clip plane, right? So we have 5 more planes that we need to check, and I'm not going to go into the same level of detail as the first one because they work in the same way. I'll just show you each slide for a few seconds, and you can pause the video and check my math, which you definitely should, and I'll be grateful if you do, because I had a lot of errors as I was putting this together. I actually asked my wife to check my math, and she was like, not gonna happen. Okay, so this check is for the left clip plane, and we say that if the dot product of the view space vector by the first row plus the fourth row, if this is greater than or equal to 0, then P is on the right hand side of the left clip plane. Then we check whether we are below the top clip plane. Okay, if the dot product by the second row minus the fourth row is less than or equal to 0, then P is below the top clip plane. Next we have the bottom clip plane. Okay, and we get the second row plus the fourth row. It's always the fourth row. And then if this is greater than or equal to 0, then P is above the bottom clip plane. And finally, we have the far Z in this case. Okay, the third and the fourth before the far Z. And finally, the near clip plane. Okay, the third plus the fourth. And then we know that P is after the near Z. Okay, so let's see some code. And as I said, we need to do some preparations here, right? We need to combine all those rows from the perspective projection matrix. So I have a new class here called Frustum Culling, whose object is defined on the stack here. And this is okay because this is a very lightweight object, and it changes from frame to frame as the camera moves around. The constructor takes the view projection matrix. Let's see the class now. We can see that Frustum Culling has 6 private vectors for the different clip planes. The constructor takes the view projection matrix as a parameter and calls update to do the actual work. And this function calls calc clip planes, which is a function of the matrix itself. And it passes in the 6 vectors of the clip planes. And this function will calculate them and put the result back into these vectors. Okay, so they are passed in as reference. So let's see that. What we do here is to extract the 4 rows of this matrix and then calculate the different clip planes exactly as we saw. So for example, to calculate the left clip plane, we need to add the first row to the fourth row. Okay, this is exactly as we saw here. And then for the right clip plane, we need to subtract the fourth row from the first row, as we saw in this calculation. And then we continue like that. So now these vectors are all updated correctly. So the Frustum Culling object is now ready for action, and it provides a function called isPointInsideViewFrustum, very similar in principle to the first method. Let's see the context in which it is called. So previously we had isPatchInsideViewFrustum view space, so now we have the same thing, only in world space. And this function takes the Frustum Culling object instead of the view projection matrix. Okay, so let's see this function. The x and z are calculated in the same way, but for the y, we actually extract the height at the 4 corners of the patch and calculate the minimum height and the maximum height. And then we use that to create a real bounding box. As you can see here, we have the 4 corners on the bottom of the bounding box and the top. Okay, so we use the minimum height here and then the maximum height there. And now we do a check for all of the 8 points. Okay, so if one of them is inside the view frustum, then the entire patch is inside. And in this case, we use the function from the Frustum Culling object. So what we do here is to calculate the homogeneous coordinate using the position vector, same as before, and then do the dot products with all of the clip planes with the proper conditions that we saw in the slides. And if all the conditions turn out to be true, then we know that the point is inside the view frustum. Okay, so I've switched to wireframe because I want to show you that in some cases the algorithm fails, as you can see in the bottom left corner, where with a small move of the mouse, the patch appears and disappears. Now, I've been debugging this for a while, and I think that the problem is that in some cases, the patch, or at least some of the patch, is inside the view frustum, but none of its corners, or the corners of the bounding box, are inside. So in this case, when I'm playing with the mouse, I'm moving in and out one of the corners of the bounding box, and this causes the patch to appear or disappear. So obviously this is a pretty bad anomaly, and it seems like terrains are less forgiving in that respect compared to regular objects. So we can probably solve this by extending the size of the view frustum by something like 10 to 20%, but we need to do more math to decide exactly the size of the safe area. Another option is to check for an intersection between the planes, the 6 planes of the view frustum, and the planes of the bounding box. Okay, so instead of checking for corners or points, as we did here, to check for intersections of entire planes, and I think this will solve this problem as well. Now, obviously, this is more complex, so I think it will have to wait for a future tutorial, and in the meantime, thank you for watching.
Do not fire until fired upon.
I thought you said do not render until rendered upon.